thank you very much, Pier Domenico, for the introduction. And let me thank, of course, the organizers and also all the TDS community for the opportunity to give this talk. I would also like to thank all the people at City Lab and very many other friends and colleagues that I met along these 25 years already. Indeed, the age increases. And today is maybe a talk about what I tried to learn in these years about time-delay systems, and the outline is basically given by the subtitle, so it's a journey through the most important elements of semigroup theory in the field of delay equations, and also a little bit about their discretization, even if I wouldn't say that this is a talk centered into the numerical analysis point of view. Let me start from something I assume you know very well, and this is a very general framework for autonomous deterministic motion, mostly in the linear case, with a bit of historical perspective too. So if you think to autonomous motion, maybe you have in mind a time map which goes from a state space X into itself, and just send some initial state into the state at the current time t. And no way that this time map should satisfy these couple of properties that I call a functional equation. So the first one is basically saying that I can reach time t plus s directly, or first moving by time t and then by time s. And the second one is just saying that without time, there is no evolution at all. So the family of all these time maps for time greater than 0 or equal than 0 is called a semigroup. And the name comes from the fact that actually it moves the additive semigroup of the non-negative reals into the multiplicative one. And historically speaking, it was first John Napier to be interested in this kind of equation, and that was the birth of what we call today the slide rule, or the logarithms, indeed, which is a smart way to transform products into sums. And in a seemingly completely different setting, we have this simple linear differential equation, perhaps the most famous ordinary differential equation. And we all know the solution is the time exponential with exponent a, which characterizes the right-hand side. And here it was Leonhard Euler interested in studying these kind of equations for the sake of investigating the dynamics of compound interest, of accumulation of capital under compound interest. But this marked basically the birth of exponential functions. Then it came Agustin Cauchy, who in his treatise in 1821 asked to solve this problem. So try to find all continuous maps T that satisfy our functional equation. And if you work a bit on the problem, you will realize that continuity is enough to provide smoothness. And actually, the only possible solution to this problem must be an exponential function with a given particular number A. And there's no other solution under the framework of continuity. So there's a link between the two problems. So the semigroup satisfying the functional equation and the exponential function satisfying the differential equation. And the link is actually given by that specific number A, which is actually the derivative of the semigroup at time 0. And following the beautiful monograph of Engel and Nagel about one-parameter semigroups, they comment about these two objects by saying that the semigroup is somehow a permanent change of time, while the number A, which is called the generator, reflects the eternal, timeless principle behind. The name semigroup should be clear. Maybe the name generator is a bit exotic, but if you take again the functional equation in relation to the differential equation, and the relation is given by the exponential function. Well, of course, I'm treating the real scalar case. It's just the beginning, and this is easy to understand. But in general, the semigroup is not known because it's implicitly defined by the solution. And but those were the times where calculus went on. So the attention was moved into understanding infinitesimal changes at the local scale. And so it's easy to differentiate the known solution u of t at time 0 to get this number 8, and note that time 0 is enough because we are talking about autonomous systems. But it was truly a vision of Lagrange, by which today we know that differentiation actually generates time translation. And the vision, even at that time was not so rigorous, is to see this part here as the series expansion of the exponential of the differential operator at time 0. If you work it out formally, it is really like that. So from here, you recover that this link between this number a and the derivative at 0 of the semigroup. So a last thing before moving to the second part into delay systems is to consider not only linear problems, but also some forcing term B. And the problem here is whether you can express your solution U in terms of the forcing function B, and of course we know the answer. The answer is given by this fantastic tool, is the variation of constants formula, which is very important if you want to derive many results in dynamical system theory, like the principle of linearized stability, bifurcation analysis, and so on. But alternatively, if you think about the semigroup of the problem 1, if it is well posed, of course there's a semigroup S behind, you can call lambda this special number, and yeah, you can solve the problem in this way here, where the red part is what we call today the resolvent of the problem. And actually, it can also be recovered by this integral on the half line, referring to the original semigroup of the homogeneous part, and that's what we call the Laplace transform. So when we go to delay systems, a big question is whether they are finite or infinite dimensional dynamical systems. Let me show you three elementary examples by which we understand that a finite dimension is not enough to understand delay. And the first one is the so-called shower example, or it is the negative proportional feedback. And if you increase the coefficient k in the positive line, then you will exhibit non-monotonic behavior. And in the ordinary case, without delay, to experience a non-monotonic behavior, you need at least dimension 2, while this is a scalar problem. And if you go through some non-linear right-hand side, like in the case of the Mackey-Glass equation, you can reach even a more strange situation, like seemingly chaotic behavior. But without delay, you would need at least 3 equations. And even more simply, if we consider the highest equation, so the basic linear right-hand side, which depends on the present and on the past, and you try to substitute for the exponential function, you get the characteristic equation, which is very well known. But unfortunately, this problem is nonlinear, and the nonlinearity comes from the presence of the delay, is the red term in there. And we all know today that this problem has infinitely many solutions, they call characteristic roots. And for that, we, of course, would need infinitely many ordinary differential equations. So it was since the seminal works of Krasowski in the 50s that we today know how to write a proper initial value problem for a delay equation. Again, in the linear case, so L is a functional from our state space X into Rd. D is the number of equations. We need properly a whole history function in the delay interval, is this function phi, which properly completes our Cauchy problem. And the right-hand side, expressed in a general way, depends on this function x sub t that we all know to be the state of our system. And this is the shift of the trajectory between time t and t minus tau back into the original delay interval. And the basic theory, the classical theory, chooses space, the space of continuous function. And indeed, already in the definition of this function, you see 2 dimensions. We have what I call the physical dimension d, basically the number of equations of the problem. But again, we understood already from the 3 examples that the dynamical dimension is infinity. So the object evolving in the state space is not a vector, but rather a function. And when we come to compare ordinary differential equations, even in RD, with delayed differential equation, we still recognize the action of a semigroup, of course, if these problems are well posed. But if in the ordinary case we know everything, because we have the matrix exponential today, and this result is due to Peano in the late 19th century, 18th century. And what about the semigroup for delay? Well, of course, if the state space is a space of functions, it is infinite dimensional, which means that also this operator must be infinite dimensional. So when we try to extend the notion of generator, we cannot resort in general to the exponential function. But alternatively, we have at disposal this second definition of the special number A, that in this case now is a matrix, A to the left. That's the derivative of the semigroup at 0. So this definition can be extended, and it is actually the modern definition of the so-called infinitesimal generator that operates between the state spaces, from the state space into itself, and it's really defined as the limit of the incremental ratio. So that's the standard definition of derivative at 0. But of course, we should require that the limit exists, and this gives you the domain of the generator. This is the very general definition for any semigroup, that it is at least strongly continuous, but strong continuity is not unless that if you want these to make sense, the numerator should vanish, because the denominator is vanishing. So that's the requirement of strong continuity, which is abbreviated as C naught later in the slides. And if you think about our problem, our DDE, you can work this definition out and you get the generator as the differential operator with a special domain of C1 functions which satisfy this condition. And this red one is the only point where the original model enters the scene. So there was already an extension to the exponential function in the for infinitely many ordinary differential equations, but under a certain boundedness condition, and this was done by a student of Peano, Maria Gramegna. But the problem with delays is that our operator A is in general, it is, not in general, it is unbounded. So if you try to expand the exponential function in power series, you cannot do that. So that object is meaningless. So the proper description is to use this so-called abstract Cauchy problem. So on the left, we have still our ordinary differential system, and on the right, we have the abstract description of the delay differential equation, and you now can compare completely the two problems. The only difference being the fact that the quantity evolving in the ordinary case is a vector of dimension d. So in the ordinary case, the physical dimension coincides with the dynamical dimension. But in the case of delay, the dynamical dimension is infinity, and it does not coincide with the physical dimension in general. That's the problem. But still, if you describe delay equation in this way, everything is similar to the ordinary case. So you have a semigroup law moving the initial state into the current state at time t. You have a generator, which is always the derivative of the semigroup at 0, and you have a bunch of results following this description, which are basically equal. So for instance, stability, we come to know about stability by looking inside the spectrum of the generator. Okay, there are also many other ones of this kind of results, and even some can be a bit of a strange flavor, like number 5 there. But if you can interpret the action of the generator A as differentiation, then that maybe difficult result is just a version of the fundamental theorem of calculus, is nothing else. So we understand now that, of course, as we already know, that delay systems are infinitely many ODEs, said in a very rough way. So in an attempt to compute something from the practical point of view, a natural idea is to use just a number of these ODEs. So we go back from the infinite dimensional space to the finite environment. And as an example, I described the computation of characteristic roots. Of course, those lambdas are in the spectrum of the generator. We know that for standard problems, this spectrum is just a point spectrum, so the equation to be satisfied is this one, but A of phi is just differentiation, and the solution, again, is an exponential function. So it's true, eigenfunctions for delay problems of this kind are exponential. So you still see there's an exponential action behind the dynamics. And to go to finite dimension, in a very general perspective, we just need a finite dimensional discrete space and two operators that bring us from the infinite dimensional state space X into this finite dimensional counterpart and backward, possibly in a more regular space, pi m, subspace of the state space. You can think about polynomials, for instance. And the way to reduce the generator to finite dimension, independently of the method you have in mind, independently of the choice of restriction and prolongation, is always to restrict the exact action of the operator, which is differentiation, as applied to the prolongation of your vectors. And of course, you have to take into account that you have a boundary condition characterizing the domain of the generator, so you should also include this condition when you discretize your problem. So just a side comment is that whenever I talk about discretization, I will use lowercase letters for functions in the infinite dimensional state space and corresponding uppercase letters for vectors in the finite dimensional discrete space. But this will come back later on. So this is just a general receipt to go from the infinite to the finite, and indeed, in the last 25 years, there have been, and even more, there have been a lot of methods based on this point of view, and let me start just to mention a few of them from DDA BIF tool. The first version was based on discretizing the semigroup through linear multi-step methods, and once I have a discretization of the semigroup, I can use that to approximate the derivative of the generator simply by the incremental ratio. That's the first choice. Then a few years later on came pseudospectral methods, and nowadays DDA BIF tool gives you the choice to apply also these kind of methods, and for collocation, just to give you an example, restriction is just evaluation at Chebyshev nodes, while prolongation is Lagrange interpolation. But under the same framework, you can describe a lot of methods, like methods based on weighted residuals, like it is described in the paper of Leotsky and Nisperger, where restriction is getting the coefficients on a Legendre basis, while prolongation is just the truncated Fourier Legendre series. And I apologize, I tried to collect many names of people working on this kind of tools, trying to approximate maybe roots, multipliers, or other interesting quantities, but for sure the list is not complete. I want just to underline that the idea of passing from infinite to finite is very old. Once we understood this for delay, first methods appeared maybe in the 80s. I remember these papers of Ito and Kappel about using spline functions to get approximation. So today I don't want to focus on any specific method. I'm rather more interested on the step from infinite to finite, independently on your favorite choice of restriction, prolongation, and finite dimensional state space. So the question I would like to ask is, what are the important features to consider when you're going to make this step? And I have to say that after a few years, I feel quite safe in answering that there are at least three key aspects. First of all, the spaces where you're working on together with their norms, because since you are in infinite dimension, norms are not equivalent. So the way you measure your objects make a difference. And then for delay equation, fortunately, there should be somewhere a regularizing effect. And this is a key element. And as a last element, we need to choose proper numerical methods, proper in the sense that they should be consistent with the 2 points above. So they should be related to the particular state space I'm working on and to this regularizing effect. So before going on, I want to just show you an example that depending on these choices, you might have surprises. And I borrowed this example who Jan Sieber discussed in the TDS webinar last March. And I'm thankful to him for giving rise to this example. So this is a linear delay problem which has a double eigenvalue lambda bar in -1, and all the other roots are with the real part at -infinity, independently of the choice of tau. And if you try to apply collocation, you will get always spurious negative roots. You can get good approximation to lambda bar, which are the important ones, but you get also other things that should not be there. And the explanation for this is a question of machine arithmetic that goes back from a paper of Trefethen in the 87 about spectral methods for partial differential equations. And then you can extrapolate an explanation that applies also to delay systems, where you see that you will lose all your accuracy if the real part of what you are trying to approximate is to the left of roughly that number, that is the logarithm of the machine precision divided by tau. So what happens? It happens that when we are trying to approximate all the roots at -infinity, to get something reasonable, tau should be 0. But of course, it is not 0. But still, and this is to me is an important message, even if a computer cannot know anything about the original state space because it is an infinite dimensional state space, it only knows about discrete spaces and vectors, but still that, the computer feels there's something going on. Indeed, if you try to decrease the delay, as in the picture here, from 110 and 1, you see these spurious roots, which are all the other colors other than the green one, which is the correct one at -1, they move to the left. So they, in principle, would reach -infinity as tau goes to 0. And the reason behind is basically that 1, I would say, is a spurious delay equation. It's not really a delay equation because from the second you recover that y is the exponential, and so you can plug it in the first and you see you get an ODE with a forcing term. And there are only 2 eigenvalues at -1. So all the construction is quite spurious, but still good to know. And if I gave a comment on computers, let me just give a comment on humans. That, yeah, it's really important to set the proper state space for the problem at hand together with the norm. And this is important both from the point of view of the theory of dynamical systems as well as from the point of view of trying to prove convergence of discretizations. And here I just mentioned a couple of examples where things might go wrong. And for instance, if you consider the initial function phi hat giving rise to the fundamental solution of your linear problem, which is the trivial function on the delay interval which takes value 1, or the identity in dimension d, right at 0, well, that function is not in the state space. Of course, it is not continuous. Another completely different example, if you want to treat the theory and also the computation of Lyapunov exponents, you need to rely on orthogonality. And there's no orthogonality in the space of continuous functions. So you need to change space, and there is this product space, which is also very used in the control community. So far I talked about linear autonomous evolution, and now I would like to make a jump further, and I have 2 directions. I can either consider nonlinear autonomous problems, but I will not in this talk. And I'm going to refer to the paper 4 and the preprint, which is on Archive, now number 30 by Davide, Francesca, and other colleagues. And so this started around 10 years ago, and now we are, they are releasing a new version of MathCont, which includes the possibility to treat also delay equation through this pseudospectral collocation. But rather, I want to focus now on the other direction, which is still linear, but non-autonomous problem. So where my right-hand side depends on time t beyond the dependence on the solution itself. And well, we don't need much motivation. There are models that are intrinsically linear and periodic, like the celebrated delay-matrix equation. Or we come down to this model when we want to address the problem of local stability of a periodic orbit, of a nonlinear problem, or maybe even more, some generic orbit. And with the term generic here, I mean neither constant nor periodic. And well, we all know that the big difference between autonomous and non-autonomous evolution is that in the first case, it doesn't matter where you start your evolution from, but only the past time matters. So the difference between t, the current time, and s, the starting time. While in the non-autonomous case, both t and s make a difference, so they are really independent. So it's not surprising that after this observation, we need to extend the semigroup notion to a notion of two-parameter semigroups. So there's a family of evolution operator which depends on both the starting time and the current time. Of course, they always work from the state space into itself, and the meaning is always the same. They move your initial state at time s into your current time state. And we do expect they satisfy the basic law, the basic functional equation, and this one is just a slight modification, but it has the same meaning of the original semigroup. So our goal here is to approximate a time step h forward in time, starting from s, h is positive. And this is very general, because if you have an autonomous problem and you take s equals 0 and any h, you recover the original one-parameter semigroup. And maybe you go investigating the spectrum or its generator or whatever. If you have an omega periodic problem, you are interested in the so-called monodromy operator, which is the operator advancing the evolution of one period. But if you are dealing with generic non-autonomous problem, you might go to the theory of Lyapunov exponents, and then you might be interested in a sequence of operators along an increasing time sequence, Tn. So you can read about evolution families in those two beautiful books by Ciccone, Latushkin, and again Engel and Nagel, that by coincidence they were published in the same year. And I remember that Ciccone published a third book the same year, so that was quite crazy. And we dealt in our group with the discretization of these families in 2012 about delay differential equation, and more recently in 2018 about renewal equations. But today I'm going to talk a more general framework, and it's a work in progress with Alessia Davide and a recent master student, Giusy Bosco, who's not here. And to understand this, I don't want to use formula. I just show a figure which I think is more representative, and I thank Davide to provide me the figure. So first, I shift the time s to 0 to deal with the evolution from 0 to h, but then I will recall that this starting time is in the right-hand side. And so what is the action of my evolution family is to take an initial function, phi, the red segment here, and move it into the state at time h. But the state at time h is just the shift back of the piece of solution in yellow between times h and h minus tau. And the solution is described with the information given by the problem. So a delay problem gives to you two information. First is the initial function, so the history, phi. And second is something that we don't know, but it is given by the equation itself. It's the information granted by the right-hand side. Is what I call z. It is an unknown in principle, but just understanding how z is got, we can understand the problem. So our z is given by the right-hand side through this function f, which I will define with examples later on, and the right-hand side is of course applied to our solution, which is again this operator s. So I decouple the problem into the action of the evolution family and the information given by the equation z. And the second one is a fixed point equation that I assume to be well posed because the original problem is well posed. And the other important thing is that all these operators, v, s, and f sub s, works into three different spaces. First, the first one is the state space x, which are functions defined in the past. Then I need a second space x plus, which are functions defined in the so-called future between 0 and h. And then I need also a third space, which is somehow the union of the two. So I have functions defined from the past into the future. So just to give you a couple of examples, in the case of delayed differential equation, my operator S is just the initial function in the past. Of course, I want my solution coincide with the initial history. And being a differential equation, the information provided by the problem is the derivative of the solution. So Z is the derivative. And when I have the derivative, I just use the fundamental theorem of calculus to describe the solution. But when I deal with renewal equations, which prescribe the solution itself, the operator S is again the initial function in the past, but in the future is just the information itself. And for both systems, the right-hand side is expressed in this way here, where you recognize the original shift by time S into the right-hand side. Does this framework work? Well, it depends on the main ingredients, and if you want to discretize that, we need a positive integer, and we need a hierarchy of spaces. We start from our state space, then we must search for a subspace x tilde where our discretization makes sense. Just to give you an example, the standard space for renewal equation is the space of L1 functions, where I cannot work with interpolation, because interpolation requires point-wise evaluation, which is meaningless in L1. So I need some more regular space, and then I need another subspace, probably, x bar, which is more regular than the previous ones, and it is the space where my numerical method converges in the norm of the original state space. And this is the most demanding part from the numerical point of view. And then below that, I have the approximation space. So if I have functions in my state space, maybe I decided to approximate them with algebraic polynomials or trigonometric polynomials or any other kind of things you have in mind. And of course, I can represent these finite dimensional objects in a discrete approximation space that is x sub n. So then I choose my favorite numerical method on the state space, so a couple of restriction and prolongation operators with those properties here. These are important. And I have also to approximate functions forward in time. So I can choose a different numerical method, or maybe a different discretization index, but the features must be the same. And these are all the objects you need to discretize your evolution family, and the outcome is that you reduce the original formulation into a very similar formulation following the same principle. So you always apply the exact action of your operators to the prolongations of your vectors, and once you get the result, you restrict them back again into the finite dimensional space. So, and this, again, this is independent of the ingredients you would like to use from the numerical point of view. What about convergence? Well, convergence is based on the non-convergence of operators from this regular space x bar into the original state space. And about spectral approximation, there's this very useful monography of Chatelain. And the requirements to get this norm convergence is, of course, a well-posed fixed point equation, the one you need to solve to get Z. And you need some regularization, as I told you before, and this can be given either by the equation itself. If you think about differential equations, those are smoothing objects. Because if the right-hand side is continuous, it means that the derivative on the left is continuous. So you gain one degree. But if you think about renewal equations, the equation is not regularizing, and the regularization effect comes typically from the right-hand side, which is an integral, or a Volterra operator. And so you have spaces, you have this regularization effect, and then, yeah, you can choose different methods in the past and in the future, but they must talk to each other somehow. So you need to check some properties of compatibility between the two. So specifically, the method in the past should be able to represent accurately the approximation in the future, but what is really crucial is the method you choose in the interval 0h. That's the key element for convergence. And yes, So I'm not going to go into the details. And perhaps later on, if you ask, I can show you more detail. So this was the generalization towards two-parameter semigroups and non-autonomous evolution. But still there are cases where in the non-autonomous case, you can go back to the autonomous problem. And one of these cases is, for instance, the case of periodic problems. And the tool to proceed in this way is the so-called evolution semigroup, T, associated to a given evolution family V. So you want to move from a two-parameter into a one-parameter object. And the way to do that is to define the semigroup in this way. Seems a strange way, but it has a meaning. You can read about this in, again, these two books of Ciccone, Latushkin, and Engel-Nagel. But the first ones to introduce these tools in the field of population dynamics were Isashi Inaba and Horst Thieme more recently. And a nice result from this coupling is that the one-parameter semigroup and the two-parameters family have the same spectral bound. So if you're interested into stability, you can look in the simpler situation. And also, if you construct the generator of the one-parameter semigroup, the spectral bound of T coincides with the spectral Abscissa of the generator, which is in general not true. But in this case, it is so. So to show you the gain you can get by this way of proceeding, I show you an example from an ordinary differential equation, so nothing special. This is finite dimensional, and this can be interpreted as a basic model for population evolution. So you have a right-hand side which is a balance between birth and mortality, and both are assumed to be periodic, like for maybe seasonal reasons or whatever. So we can consider the evolution family V associated to this problem without fertility B. And if you have no fertility, of course, your population is going to extinction. That's the underlying behavior. So you set up a proper state space, which is the space of periodic functions with periodic L1 restriction. And following the beautiful theory of Dickman and colleagues in the 90s, we can define a next generation operator, which has this expression K here. And this is an infinite dimensional operator, but if you can compute the dominant eigenvalue, that's the so-called basic reproduction number. So it is this famous number that 5 years ago decided about our life if we were able to go out of home or not in the COVID period. So if this guy is greater than 1, we can have an epidemic break, or otherwise, no. So about the computation of this dominant eigenvalue, of course, we need to go back to finite dimension, and the first cases were introduced by Nicolas Baccaer in 2007, but he struggled to discretize this object by first computing the evolution family, which means solving the problem, and then computing integrals on the half line, which I think we don't like a lot. So in a recent work with Jordi Ripoll and my past PhD student, while he defended his thesis a couple of months ago, now he's a postdoc in Trento, Simone De Reggi, we can reformulate our problem by introducing these two operators, calligraphic B, which is just multiplication, and calligraphic F, calligraphic M, which is just the right-hand side of our original equation, rearranged. And then if we have the evolution family in principle, we can introduce the evolution semigroup, and suddenly my original next generation operator boils down to this product here. And this again is by using the Laplace transform of the original semigroup, of the evolution semigroup. What is the advantage? Well, if you want to compute the eigenvalues of this guy, you can transform these into a generalized eigenvalue problem where your ingredients are the original coefficients of the model. So you just need to discretize B and M with the method you like, and you get possibly effective approximation of R0. And of course, there's no need to compute the underlying evolution family, and there's no need at all to compute integrals on the half line, which is quite an advantage. So let me comment just on this point of view. You see, I've changed completely field of application. I've changed target. So now I'm interested in the dominant special basic reproduction number. But again, the underlying framework is unchanged. It's the framework of infinite dimensional dynamical system with all these semigroup properties. And it can give you a lot of advantages, like saving a lot of computations. And also, it helps a lot in understanding the theory in the background. And this was applied just to ordinary differential equations with periodic right-hand side in RD, but the next move is to go towards abstract spaces. And if the usual say is no pain, no gain, I would say that here is some gain, no pain, because the theory is already there. Okay, let me go into the final section of this talk. And I think this is probably new for most of us. And to me, personally, this is an appraisal of the work of Otto Dickmann and many other colleagues, but especially Schur-Verdun and Lunel. And this is about twin semigroups. I want to try to explain what are these tools, very recently proposed. And yeah, let me start with what is the challenge with delay systems from this evolutionary perspective. Well, classical delay equations come either in two forms, or you either have a delay differential equation, which means that you have a right-hand side prescribing your derivative at the current time, and the right space here is the space of continuous functions, well, the classical space. Or they come into the form of a renewal equation, which means that the same right-hand side can give you not the derivative, but rather the solution values at the current time. And here, especially from the modeling point of view, the correct state space is the space of L1 functions on the delay interval. And on top of that, you can even consider the neutral versions of these two classes of equations, where neutral, we all know it means that the delay appears also in the highest degree derivative of your problem, which is in x prime in the case of delay differential equation of first order, or directly in the solution at the right-hand side itself, in the case of renewal equations. So what are the general requirements of a state space you need to set up your theory? And the first one is you need a strongly continuous semigroup. That's necessary to get out a variation of constant formula. And the variation of constant formula is the basic tool that you need when you want to study perturbations, which includes also local behavior through linearized stability, but bifurcation theory, Floquet theory, and whatever. And strong continuity is important because it gives a meaning to the integral on the right-hand side of your variation of constant formula. And the second requirement is that you would like your initial function giving rise to the fundamental solution to be an element of the state space. Is what I call het phi a few slides ago. So it's the trivial function on the delay interval, but getting value 1 at 0. 1 or the identity in dimension d if your physical space has dimension d. And the bad news is that, unfortunately, those requirements are incompatible. And on top of that, in the choice of classical spaces, continuous and L1 functions, in none of them you can find the initial function for the fundamental solution. So the way that Dickmann and colleagues propose to overcome this problem in the monograph of 1995, the big yellow book, and then later on for renewal equations in a paper of 2007, was to resort to the so-called sun-star calculus. I want to just give you an idea, and the idea behind is trying to keeping strong continuity, renouncing to your initial function for the fundamental solution in such a way to enlarge your state space in order to accommodate this element that naturally is not in that state space. So the way to do that, briefly, is to go to the dual space of the state space, what I call X star. In that space, the dual semigroup is not strongly continuous. So you must restrict the domain to a space X sum in order to gain strong continuity again. And then you would like to go back to the original state space by taking the dual again. So you go from X sum to X sum star, but again you lose strong continuity, and again you restrict to this space X sum, where now the semigroup is definitely strongly continuous, and your new space X sum is large enough to have the initial function you would like to have. And then all the book is about the treatment of delay equations as perturbations of an original, possibly trivial delay problem, which is described here through the generator, so in the abstract form. You can think, for instance, to the trivial delay equation x prime of t equals 0, or to the renewal equation x of t equals 0. Of course, those are well posed, and you can get a semigroup T naught, which is the basic element, and then you study perturbed problem at the level of the generator. So you consider the generator A of the problem you want to study as the generator of the trivial problem plus some perturbation B. And indeed, you can prove under this theory that you can construct a well-posed variation of constant formula, which might look scary, but it works very well. And the integral here is a weak star integral, and J is the embedding from the original state space into this star space. So this beautiful, elegant theory is quite difficult, at least to me, but it works. It works for delay differential equations. It works for renewal equations completely. So based on this theory, we could prove the principle of linear stability in the autonomous and in the periodic case, bifurcation theory, and whatever we like. The only problem is that it doesn't work for neutral equations, because the neutral problems are described by unbounded perturbation B. So somehow they were not satisfied, and they introduced recently, well, at least it was published in 2021, this paper on the Journal of Differential Equations by Odo and Schurd, about this new functional analytic framework of twin semigroups, in which the idea is the opposite way. So now we would like to not consider strong continuity, but we would like to work on spaces larger than the original spaces in order to have the initial function of the fundamental solution. Of course, if we renounce to strong continuity, we have quite a few disadvantages, like our operators in general are not compact, not even eventual compact. And as a consequence, we cannot use spectral mapping theorems, which are the standard tools. We go from the semigroup to the generator at the level of the spectra. And on top of that, I would say that twin semigroup theory is even more difficult than some star, if possible, but it seems like that. But of course, there are advantages. And for instance, one big advantage is that we don't need a notion of differentiation to understand our generator. It's rather based on the concept of Laplace transform, and the Laplace transform is based on integrals. And the point here is that differentiation requires maybe too stringent conditions to our functions. So in this framework, they've been able to get a properly posed variation of constant formula, where now the integral is a Riemann-Stieltjes integral, and they got result about asymptotic behavior of the related semigroups without using spectral mapping theorems. And to me, one of the most amazing features is that now delay differential equations and renewal equations are two sides of the same medal. So really, it's just enough to exchange the two twin spaces, and the theory is completely unchanged. Finally, and that was the reason why this theory was hardly introduced, is that it can tackle also the case of neutral equations, both neutral differential and renewal equations. Of course, there are a lot of open questions following this article. So for instance, all the consequences of using the variation of constant formula. So there is still no principle of linearized stability based on this theory, but the author says that, yeah, they are quite confident that everything can be proved, and that's quite hard. And from the numerical point of view, there's nothing basically about that. It is our project in Udine to try to set down a proper discretization framework in the general meaning I try to talk to you about today. And I'm working on that with Davide and another master student who's going to graduate in a couple of weeks. Yeah, I think it's time. Well, first, before closing, let me just give you an idea of why neutral renewal equations are important. They are important in population modeling, and there is this first, between commas, trivial case of cellular division in the work of Odo and Sherd. And together with Sherd and Davide, we investigated this less trivial problem where the function f at the right-hand side is periodic with the period equal to the delay of the problem. And of course, you can see from your equation that there is no regularizing effect at all. And this means that the monodromy operator in the background is not compact. And indeed, the spectrum is not only point spectrum, there's also a residual spectrum. But the nice result is that we can characterize the spectrum by using the coefficient of the right-hand side. It is the closure of the range of the function f. There are also some hints on how to work with systems and multiple delays, but there is no convergence theory at all. We have not been able so far to prove anything because it's like to have a sequence of compact operators, those you are using on the approximating spaces, converging to an operator which is not compact. And yeah, but there's a lot of numerical evidence on how things work, and perhaps a perturbative approach is the right way to tackle this problem. So I think it's time to close and try to show you, at least in the framework of semigroup theory, what can be the challenges, but of course delays are a source of several challenges, the most of which have not been even mentioned today. But there is still one I want to talk about, not today, but maybe tomorrow I'm going to give a talk in place of my student Mohamed Tanvir about data-driven methods. And I think this is quite a new perspective. Well, if not new, it's recent, and it's a completely change of point of view because this is not based on models anymore, but the other way around. We just try to use data to recover perhaps the right-hand side describing what we think it is a model behind the dynamics. There is quite a few people working on that, and some are in the audience, like Gabor. But in any case, a couple of general messages is, of course, delay systems are difficult, and difficulties hinder the use of realistic models. That is what we should need to describe reality, especially in the context of biology or population dynamics. And I'm definitely convinced that interdisciplinarity is a key issue, and we have a proof this morning in the plenary talk of Professor Kassak about the biological implications of control and delay. And when I think about interdisciplinarity, I'm not talking only about mixing different fields, but also about mixing theoretical and practical or computational aspects, which should not be divided. And I think that's all by now. And I really would like, again, the TDS community, our community, and because it's constantly fostering decisive progresses in these and related fields. And I really appreciate two features of this community. First, it is really open. It's really open to several disciplines, and this is very good. And also I appreciate a lot the support it constantly gives to young students and researchers, and that's really important and valuable. That's all. Thank you very much.